There, and welcome to another video for the course of algorithm design. This video is another video in a series in which I solve the same dynamic programming problem in several different ways. In this video, we're going to solve it in a forwards manner in 3D, whatever that means. Before we look at the solution I have in mind for this, please make sure that you are familiar with this problem. And if you have not tried to solve the problem yourself, pause the video now and really try to solve the question yourself first. These videos are utterly useless if you haven't at least spent a couple of minutes trying to play around with this problem by yourself first. Learn by doing rather than by watching. So with that in mind, pause the video first, try to really solve it, then continue watching and see how I would solve this in a forwards manner. All right. So for this problem, what have we got? We need to write an n-line poem about m special events. And each line should describe an event. And an event should have at least one, but no more than k lines talking about it. Now, each line-event combination gives us some emotional value, and we want to maximize the emotional value. Okay. One way to reason about this is to say, well, what happens at the start? What happens when we get to line number 1? Well, line number 1 needs to be about event number 1. After all, we may not skip any events. Each event should have at least one line on it. And each line should describe an event. So for line 1, we have no choice. But what happens when we get to line number 2? Well, when we get to line number 2, we do have a choice. We switch to event number 2, or we stay with the current event. Now, what I'm going to try and do is I'm going to take this choice that we have of staying with the same event or switching to the next one. I'm going to write down a mathematical function opt, which encapsulates this behavior. So what does that look like? Well, we're going to want an opt function. And this opt function is either going to have the choice to stay with the current event or to change the event. And how can we then encapsulate this in opt? Well, like I mentioned, if we are at line number 1, we have no choice. Line number 1 should be about event number 1. But then when we get to event number 2, we can choose. So what changes when we go from 1 to 2? Well, what changes is what event are we looking at? So this should probably be one of the parameters. Sorry, not what event, but what line are we looking at, right? When we change from line 1 to line 2, we should have something to indicate that we are now talking about line 2. So let's make this our parameter I. And I represents the current line. Now, when I stay with the event, or when I change the event, for the parameter I, this doesn't matter. In either case, it goes up. And we move on to the next line. But what does change is the event. So in order to make sure that our opt function, that we can indicate that something is changing, we must have a second parameter. We must have a parameter j to describe the current event. And if we stay with the event, j does not change. But if we change the event, then we move on to the next event. So we should increase it by 1. Sorry for being inconsistent in my writing of 1. And regardless of which option I choose here, we've already decided to make the current line about the current event. So that's the emotional value I get. And additionally, well, there's the rest of the lines that I can deal with. And whichever one gives me more value is the one I want. In one of the other videos I made, I now start to reason about the base cases. But in this one, I want to save the base case for last to also show you that even here, there are multiple paths in which you can get to a final solution. So here, I first want to think about what happens, what do we do with this k lines stuff? Well, what do we do with this k line stuff? what we do is we need to make sure that we never cross this boundary. So staying with the event should only really be possible if we have not yet spent k lines talking about this event. So in order to make a choice here, I need to know how many lines have I talked about this event so far. So we're going to need another parameter. And normally I would call it k, ijk, but k is already used here. It's also the capital letter K. So because my handwriting is terrible and I can't really distinguish between my lowercase k and my uppercase k, I'll call it alpha instead. And alpha is the number of lines about j so far. So how many lines have we already spent talking about event j? Now, if we stay with the event, how does our parameter alpha change? Well, if we stay with the event, we should increase it by 1 to indicate that we have spent one more line talking about this event. But if we change to the next event, then, well, how many lines have we so far written about event j plus 1? Well, so far 0, because this line was still about event j. And now let's think a little bit about edge cases, border cases, base cases. To start, let's continue with this alpha, because increasing alpha by 1 is all very nice, but that's only allowed if so far we have written no more than k lines on it. As soon as we've written k on it, we may no longer increase it by 1 and move on and stay with this event. So what should we do? Well, similar to in knapsack, where if taking an item would get us to go over the limit, we should have an explicit case here that says, well, sometimes we don't have a choice. Sometimes we must simply move on to the next event and start afresh. And when must we do this? Well, when alpha equals k minus 1. Because when alpha equals k minus 1, at this point, all I can do is still assign this line to this event if I want to. Actually, this is not correct. No, let me change this slightly. Okay, no, let me first explain why this is not correct. What I'm saying here is when alpha equals k is k minus 1, I don't have a choice. But this is not true. When alpha is k minus 1, I still have a choice. Because after all, I'm still allowed to have k lines on this topic. So there's two things I could do to change this. Either I could say, okay, when alpha is k, I don't have a choice anymore. When alpha is k, I must move on to the next event. And this I can now model in two different ways. I can either say, okay, because the current line cannot be about the current event anymore, I make the current line about the next event. And then, rather than having 0 spent on this so far, this work? Yes. I have 1 line spent on this event so far. After all, I've spent line I on this event already. So this is one way to fix it. Alternatively, we could also say when we are at alpha equals k, when we've already spent k lines talking about this event, what should we do? Well, this line needs to be about the next event, about which so far we've written 0 lines. And by not changing the parameter I, we just get into the next case now. We stay with the current line, but we move on to the next event. It's also a way to make this work. And if you've already seen the backwards video, you will see that there is yet another way to make this work by making this one of our base cases in which we return a big penalty, which I'll get to talking about in a moment. But these are at least two ways in which we can handle this case. This case where we have already spent the maximum number of lines on the current event. Now, what about the other base cases? Or what about the base cases, actually? These are all recursive cases, after all. So we need base cases. At some point, we need to stop. Well, if We have talked about all of the lines, so we are now at a non-existing line. And at the same time, we have also talked about all of the events, so we are now at a non-existing event. Then there's nothing more we can do. We should return 0. There's no more value to be gained. But what happens if we are at a non-existing line and we are still at an existing event? Well, then we have a problem, because that means we've run out of lines, but there are potentially still events to talk about. This is a situation we really want to avoid. Now, because this is a maximization problem, how do we get to a situation we really want to avoid? How do we get rid of that? Well, what we want to do is basically we want to make sure that we put something here that ensures this is never picked, that the alternative option is always better. And in a maximization problem, how do we make sure a certain option is never considered? Well, simply by making it return minus infinity. Whatever the other one gives us will always be better. Or at least it will never be worse. So this is what we should do when we have run out of lines, but there are potentially still events left. But of course, the other way around, if there are still lines left, but we have, notice how I use an and. Remember reasoning and logic, but it's just a fancy word for and. And we have run out of events. Well, this is just as problematic, because each line should be about an event. So when we've run out of events, but there are still lines left, we have a problem. And there we go. This would be a solution to this problem, where we reason forwards, by which I mean we should call this function starting from line 1, event 1, with 0 lines written about it so far. And we stop when we have run out of lines and we have run out of events. As I mentioned before, this border case can also be encapsulated in the base case still. What we could do instead is we could add here the case where if alpha is bigger than k, indicating we have written more than k lines about an event, in that case we also want to return minus infinity. This is also a case we desperately want to avoid. This is another way to handle what we are handling with this extra base case, or this extra case, rather. So there we go. This is a forwards method in 3D, because we have 3 parameters. So an iterative approach of this would have 3 dimensions of our memory matrix. And it's a forwards way to solve the problem. Now, in all honesty, for most problems, I consider the backwards way the easier one to reason about, because the problem keeps on getting smaller. Here, of course, the problem also gets smaller, but the parameters get bigger. To me, that's always a little bit confusing, but it is a totally fine method to make it work. And maybe for you, this clicks much more easily than a backward solution does. If so, great, stick with this one. It's totally fine, totally legit, and totally usable. If you've watched this video and you think, this doesn't really make sense to me, well, there are at least 2 more, but potentially more videos than that, in which I solve exactly the same problem with a different function. And maybe one of those makes a little bit more sense to you. I hope that this video, or one of the others, helps you to gain a little bit more insight in how I would tackle these dynamic programming problems. And I'll see you around for the next one. Bye for now.